Hi everyone, welcome back. Today we're going to understand very important topic from the electromagnetic waves, which is how electromagnetic wave behaves inside the dielectric material. That is, if we send the electromagnetic wave through a dielectric material, which might be some glass or the distilled water or the mica, but there are certain assumptions actually we take here. There are certain assumptions we take that the dielectric material should follow, and then we'll try to see the behavior of the electromagnetic waves inside that dielectric material with certain assumptions. Okay. And then what we'll write, this would be the first thing. We'll discuss certain assumptions, then we'll discuss Maxwell's equations become how the Maxwell's equation become in case of electromagnetic waves in dielectric material with certain assumptions. After that, we'll try to write the wave equation. Wave equation. We'll also try to see the speed of wave, speed of EM wave in the dielectric material, but with certain assumptions, obviously. Dielectrics. We'll try to see average energy density, average energy density. We will see intensity. So basically, these are the topics for this video. Actually, these are actually all are very important. Now, before going into the assumptions and then writing the Maxwell's equations, then writing the wave equation, let me tell you a very different thing, that is general Maxwell's equation. General Maxwell's equations. Then you'll understand this point easily. Okay. How the Maxwell's equations change when we apply the assumptions. Before going into the actual topic, let me recapitulate certain things. So first, general Maxwell's equations. I hope that every one of you knows del dot of E is rho by epsilon 0. Then del dot of B equals 0. Then del cross of E is minus dou B by dou T. Fourth is del cross of B is mu 0 J plus mu 0 epsilon 0 dou E by dou T. These four equations has nothing to do with this topic. Okay. These are the general Maxwell's equations. This is the Gauss law. This magnetic monopole doesn't exist. This is Faraday's law with lenses correction. Incorporating lens. This negative sign comes from the lens actually. And this one is Ampere's law with the Maxwell's correction. This part is the Maxwell's correction. Okay, I hope you all know this part. Now we'll write the Maxwell's equation. Maxwell's equation in dielectrics. Dielectrics. That is how Maxwell's equation become, how these equations become when we take the dielectric into consideration. Okay, this has nothing to do with the topic. Then we will see how these Maxwell's equations, which we are going to write, how they will behave when we apply that to the electromagnetic waves inside the dielectric material. Okay, so first one becomes del dot of D equals rho F, where D is the electric displacement. And second and third equation remain the same. Del dot of P is 0. Del cross of E equals minus dou B by dou T. And fourth becomes del cross of H equals JF plus dou D by dou T. These are the Maxwell's equations for any dielectric material. Obviously, see, while going, so only first and the fourth equation changes. So while going from this to this, and while going from this to this, they are proofs. Okay, uh, I don't know whether you have gone through those proofs, but I can discuss the proofs in a very few minutes, maybe 1 minute for the one proof and another minute for the another proof. Then we'll go to the actual topic. So first topic is actually called the Gauss law in dielectrics. Gauss law in dielectric. So basically, this is the Gauss law, and this one is the modified Gauss law or the Gauss law in presence of the dielectrics. So see, there are two bound charge densities, rho b plus rho f we have, and if we try to apply if we try to apply this equation, so del dot of E equals, in place of epsilon 0 rho f by epsilon 0, I replaced rho with this thing. So del dot of epsilon 0 E, I take this to the left, equals rho b plus rho f. I hope you know this thing, and I hope you know rho b is minus del dot of p, where p is the polarization. I hope you know this thing, and while substituting this into that, so del dot of epsilon 0 E plus equals minus del dot of p plus rho f. Taking this to left and taking del dot common, epsilon 0 E plus p equals rho f. So this is called the D, electric displacement. Del dot of D equals rho f. So this is the Maxwell equation in case of the dielectrics, okay, where rho f is the rho f is free charge density. Free charge density. So this is the proof from this to this. Now we'll do proof of this thing. Okay, so let me move this part to here. Now the equation is actually del cross of b equals mu 0 j plus mu 0 epsilon 0 dou E by dou T. Now see, in case of the dielectrics, we have three types of current densities. One is, so this J is actually J free plus J bound plus, there is another which one is called the JP, which is actually the polarization current density. This one is the free current density, this one is the bound current density, and this one is the free polarized current density. Okay, JP is actually polarization current density. Those two you know. Okay, now while JB, I hope you know this from the magnetism portion, del cross of M, and well, this JP is actually dou P by dou T. This is related to the polarization. Now applying to this equation, substituting to this equation, so del cross of B is equal as mu 0. In place of J, we have three things, JF plus in place of JB, I'll use del cross of M plus dou P by dou T. I hope there is no problem in that. And plus mu 0 epsilon 0 dou E by dou T is there. Okay, now take this mu 0 to this side, so del cross of B by mu 0, and taking this mu 0 common from the both sides, so there remains only JF plus del cross of M plus dou P by dou T plus epsilon 0 dou E by dou T. I hope there is no problem, where this B by mu 0 is actually H, not yet H. Okay, just give me a second. Take this curl common, del cross of B by mu 0 minus M equals JF plus epsilon 0 dou E by dou T plus dou P by dou T. Okay, this one is H equals JF plus, take tau by tau t common in these two, we can write it like epsilon 0 E plus P. And this thing I already took here, it's T. So del cross of H equals JF plus tau by tau t of T. So this is this equation. Okay, so we got the equation. So we got the Maxwell's equation for the dielectric. Now while we know these two things, Maxwell's equation in case of the dielectric material, now we'll come to our main topic, which is electromagnetic waves inside the dielectric. And now we will see how these equations gets modified. Okay, how these equations gets modified and how they become in case of the electromagnetic wave in the dielectric material. But there are certain assumptions. Let's move to the topic and let's write the first assumptions. So basically there are 4 or 5 assumptions in case of this topic. First assumption is the dielectric material should be linear. Okay, another is that material should be homogeneous. And there is another assumption, material should be isotropic. And what does all these terms mean? That is, if the material is placed in the external electric field, okay, then that the polarization in case of that material is epsilon 0 chi e and external electric field. This equation should be followed by the material. That is, the polarization in case of the material should be directly proportional to E. That is, the relation should be linear. That is, P should be directly proportional to E, or like, P depends on E to the power 1. In case of the non-linear, so polarization is sometimes, chi is directly proportional to E to the power 1 plus beta times E to the power 2. So the relation is not linear. Okay, so the material should be linear. That is, polarization should be directly proportional to the electric field to the power 1. This is the first assumption in case of the electromagnetic waves inside the dielectric material. Okay, second assumption is the isotropic. That is this one. Second one is the homogeneous. That is all points. So what does homogeneous mean? It means all pointers at all pointers property should be same. Okay, properties are same. That is, no point is preferable, every point is same. If we have if we have some point inside a dielectric material, and if we have some other point, the property should be same. So that is what it means to be homogeneous. And another thing is the isotropic. That is, in every direction same properties in each direction. In every direction, that is, no preferable direction. What it means is that x-axis, y-axis, z-axis, in every possible direction, the properties remain the same. No preferable direction. That is, x-axis has no preference over y-axis, y-axis have no preference over z-axis. Okay, these are certain things. And second assumption I should take now. The second assumption is that rho free, rho f, or rho f is equal to 0 inside the material, and J free, that is free current, or JF should be 0. That is, both current density, free current density, and the free current. Okay, this is the free charge density. This rho f is the free charge density, and the free current density both should be same. Now what will happen by taking these two assumptions? They will simplify actually these equations. They will simplify these equations for us. Okay, this is the second assumption. Third assumption, I should write C. Third assumption is that very important, dielectric material should be non-magnetic. What it means is that magnetization should be 0 inside the material. And there is one more important thing about the non-magnetic dielectric material is that we know mu is mu 0 mu r. This is the permittivity of free space, this is the relative permittivity, and this is the permittivity of the medium. And for this is the general for every dielectric material, but for non-magnetic, mu r is 1, so mu is mu 0. So simply permittivity of the medium is permittivity of the free space. It's as simple as that. Okay, this is one of the important properties of the dielectric material, in which we are actually studying this topic, electromagnetic waves inside the dielectric material. These Maxwell's equations are for any dielectric material with no assumption, but when we apply certain assumptions, then we'll try to write the Maxwell's equations. I hope you are trying to understand the coherence in the topic. Now the fourth one is the uniform polarization. Uniform polarization, that is, if the material is placed in any external magnetic field, then the polarization should be uniform, so that del dot of p is 0. Actually, it means this is the condition for uniform polarization. Uniform polarization. Okay, this is the very important thing. This is a very important property again for the dielectrics, in which we are studying the electromagnetic waves. These assumptions, now we'll apply these assumptions to our Maxwell's equations. Which Maxwell's equation? These Maxwell's equations, which are general Maxwell's equation for the any dielectric material. Okay, let's copy them. Let's put them here. These are the Maxwell's equation for any dielectric material, and now we'll try to see how they gets modified and how they can be written for these. So this topic is done. Which topic assumptions is done. Now we'll go to the Maxwell's equations. Okay, now B part is the Maxwell. We have to write the Maxwell's equations for electromagnetic waves in any dielectric material. I'm repeating again and again so that you understand the terminology. Okay, otherwise I have no time and no energy actually to tell again and again you the Maxwell's equations. Okay, so see, since we assume that rho f should be 0, so this is 0, so del dot of D is actually 0. This is the first Maxwell's equation. Second, del dot of B is 0. This is same. There is no problem. Third is same. Del cross of E equals minus dou B by dou T. Our fourth equation, JF is 0. Del cross of H equals dou D by dou T. Okay, here it is D. Dou D by dou T. So these are the Maxwell's equation for EM waves in dielectric material, in dielectrics, but with certain assumptions. That material having certain assumptions. So these are the Maxwell's equations. So this is the second topic. Now important thing is the speed of light concept. Okay, so see, no, before going into the speed of light concept, let's try to write actually these Maxwell's equation in terms of B, in terms of let's write this equation and this equation in terms of E and B. Let's write this in terms of E, and let's write this equation in terms of B and E. This can be asked in any examination. Okay, so this and this remain the same. So see, D is actually in dielectric material epsilon times E. Okay, and H is B by mu. Okay, for these dielectric materials with the assumptions. These are the two equations. You have to remember that D is the electric displacement is epsilon times E, and H is B by mu. So let's try to write del dot of D. So it will become del dot, in place of D we use epsilon E, and epsilon can be taken outside, and that gets divided on the right side, so that becomes 0. So del dot of E equals 0. This is again first. Second would be same, del dot of B equals 0. Third is again same, del cross of E equals minus dou B by dou T. And fourth, see, in case of in place of H, we'll use B by mu. Okay, B by mu equals dou by dou T of, in place of D, we'll use epsilon E. So this mu and epsilon combines, so which implies del cross of B equals epsilon, yeah, epsilon mu dou E by dou T. So this one is the fourth. So now these are the Maxwell's equation. This part, this part, and this part are the Maxwell's equation for electromagnetic waves in the dielectric. With that dielectric material should follow the certain assumptions. Okay, so this is in terms of D, and this is in terms of E and B. So this one is in terms of D and H, or like, first one and the fourth one are very important, and these are in terms of B and E. This is in terms of E. Now, so I hope now you get this point, okay, and this point. Now third is the wave equation. Third topic is the what happened to this? Third topic is actually the wave equation in dielectrics. Okay, see, we know general in free space it was del square E equals mu 0 epsilon 0 dou square E by dou T square. So, and in terms of B, it was del square B equals mu 0 epsilon 0 dou square B by dou T square. Now, in case of the dielectric material, mu 0 is replaced by mu, and epsilon 0 is replaced by epsilon, and permittivity of medium and permeability of the medium. So it becomes del square of E equals mu epsilon dou square E by dou T square. But there is very important thing that you should always remember, never get confused about this thing, dou square B by dou T square. If somebody tells you what is here mu is mu 0, there is no problem, because the material is non-magnetic. Okay, what is epsilon? Epsilon is not equal to epsilon 0, but epsilon is epsilon 0 epsilon r. Okay, this is very important. Okay, this is only valid for non-magnetic. For other dielectric materials, mu is mu 0 mu r. Okay, this is for this this one is for non-magnetic, this one is for other dielectric materials. This is very important. And what is the concept of speed? Now, what is speed of electromagnetic wave? Fourth part is the speed of EM wave. In free space, c was the speed of wave, which was given by 1 over root of mu 0 epsilon 0. But since we know we don't have here mu 0 epsilon 0, but rather we have mu and epsilon, so c is 1 over root of mu into epsilon. But what is mu? Mu is mu 0, and epsilon is epsilon 0 epsilon r. Okay, c equals 1 over root of, in place of mu we can use mu 0, and in place of epsilon we can use epsilon 0 epsilon r. This can be 1 over root of mu 0 epsilon 0. This is 1 over root of epsilon r. There is no problem. So c is, this is now here, this is the speed of light in free space. Now, in case of any dielectric, when electromagnetic wave goes through the dielectric material, c doesn't remain c, but it becomes v. So v is given by this, v is given by this, v is given by this, v is given by this. This part is c divided by root of epsilon r. This is very important. This equation, that is speed of light divided by root of relative permittivity of the dielectric material, we use. Okay, and we know that refractive index is given by root of epsilon r. Okay, actually a refractive index is given by for other refractive index is actually given by root of mu r epsilon r, but for non-magnetic non-magnetic, since mu r is equal to 1, so neta, or I should call it as the refractive index, is this part. So I can write this equation as V equals C divided by refractive index. So these are two very important formulas for the speed of electromagnetic wave. So this is the electromagnetic wave speed, which is given by C divided by root of relative permittivity of the dielectric material, or V is speed of light divided by the refractive index of that dielectric material. I hope you get it. Now important another is the what is next one? I believe next one is the energy density. This is the wave equation we did, speed we did, now average energy density. Okay, so let's go to the average energy density. Fifth is the average energy density, that is how much energy is present per unit volume of the electromagnetic wave in the dielectric material. Okay, we know average, we know actually energy density. This is not average, but this is energy density is 1 by 2 epsilon 0 E square plus 1 by 2 mu 0 B square. This is in case of free space. This is the energy density, not average. Okay, this is energy density, and here we can write as U equals 1 by 2, in place of epsilon 0 we can write epsilon, okay, E square plus 1 by 2 mu B square. This is in case of EM waves. This is in case of EM waves in free space, in case of EM waves in dielectrics, but with certain assumptions. Again, I'm repeating. Okay, again, remember here epsilon is epsilon 0 epsilon r, and mu here is mu 0, because the medium is non-magnetic. Okay, now we know average energy density in case of the electromagnetic waves in the free space is given by 1 by 2 epsilon 0 E naught square. Okay, this is in terms of E. There is a proof for this. I did all the proofs in the videos. Okay, or in terms of in terms of magnetic field, 1 over 2 mu 0 B naught square. This was in terms of B naught. Now this is for the EM waves in free space. If you haven't watched my previous videos, just go and have a look how I did derive all these things in the details. Okay, now for this electromagnetic waves in case of the dielectrics, so average energy density should be 1 over 2, in place of epsilon 0 we must have epsilon E naught square, 1 by 2, in place of mu 0 we must have mu B naught square. So this is EM waves in dielectrics. But remember again, epsilon is epsilon 0 epsilon r, and mu is mu 0, because the medium is again non-magnetic. So I was able to write the general energy density. This is the energy density in free space. This is the energy density is in dielectric for the electromagnetic waves. This is the average energy density in case of the electromagnetic waves in the free space. This is the average energy density in case of the electromagnetic waves in the dielectrics. Okay, now there is again another topic. There is intensity. I believe the next topic is intensity, average energy density. Now there is intensity. Now the sixth topic is intensity. So intensity is actually average of the Poynting vector. So in the electromagnetic waves in the free space, I was able to write intensity as the average of the Poynting vector, which was actually c times 1 by 2 c times 1 by 2 epsilon 0 E naught square. Okay, but here this was EM waves in free space, and now for the electromagnetic waves in the dielectrics, intensity should be V times 1 by 2 in place of epsilon 0. We must write epsilon in terms of E naught is E naught square. Okay, or intensity, there we wrote intensity as C times average of the energy density. So here we will write intensity as V times average energy density. Okay, now so this is the one of the important equations for this topic, and there are certain other terms involved. Another, I should write the momentum density. I derived the momentum density in the last topic. So there, electromagnetic waves in the free space, how we wrote the momentum density. We wrote the momentum density as Poynting vector by c square. This is EM waves in free space. So here we will write momentum density as Poynting vector by v square. Okay, this is very important. There are certain other things I should mention for the completeness point of view. So here B naught should be E naught by V. They are actually in EM waves in the free space, B naught was E naught by C. Okay, and because this is the maximum value of the electric field in the magnetic field. And that's probably all for the video. I hope you understand the video. If you haven't gone through from 5th to 7th, I think you should watch my previous videos. Thank you so much.